This says if we take like, let's say I've got some area. I'm going to look at the area. I've got this rectangular area defined by the line y equals a, the x-axis, and we're going to look at that area from x equals a to x equals b, right? So that rectangle up there is the area. Well, what do we get if we revolve that area about the x-axis? Well, then if I revolve that about the x-axis, I'm going to carve out of space a cylinder, right? That's sitting on its side. Everybody see that? Okay, if we want to find the volume of that cylinder, well, that one would be an easy one to do because it's a geometric shape, but it's a little bit tougher if the shape isn't geometric. Like, what if our upper boundary of our area was a curve and not just a horizontal line? Like if we had the function y equals f of x, and I revolve that thing around the x-axis, I'm going to create this weird kind of a shape that looks like, I don't know, what would that be? Like if I turned it upright, then it would look like a pedestal or something, right? Everybody see what I'm saying? Okay, so how do we add that up? Well, the way we add up anything in calculus is by integrating infinitesimally small pieces. We're just going to add those up. So in this case, if we take a thin slice of that perpendicular to the x-axis, what do we get? Well, a thin slice is going to give us a disk. And if we add up all those all those stacked up disks, we're going to get the cumulative volume of the pedestal, right? Okay, so how do we go about that? Well, we've got to define, if I'm going to look at an individual slice of this rectangle. Okay, so an individual slice is going to look like this. It's going to look like, we'll do orange. Okay, so if I take, there's one little slice of that area that I'm going to revolve, a little rectangle, right? If I revolve that little slice around, if I revolve that little slice around the x-axis, it's going to carve out a little disc. Looks like a little coin, right? If I added up the volumes of each of those little coins, I'm going to get an approximation of the volume of that pedestal. And if I let the thickness of that coin or the width of that slice go to zero, it's going to be infinitely good, right? Well, that's what calculus does. Okay, so then how would this work? So we want to set up for each individual coin, the solid of revolution, the radius of the coin is going to be the height of the function, right? The distance from the function to the axis of revolution, okay? Which in this case is the x-axis. So that would just be, for us here, that would just be f of x, right? That distance right there is f of x. Now in general, I like to call that distance r for radius. So we would call that something like r of x because it's going to be a function of x and it's the radius of our coins, the radius of our disk that we're creating. What is r of x in this case? Well, it's just f of x, okay? Right? So what did we create then? We created a coin with a radius of f of x, a thickness of dx. Instead of calling it delta x, yeah, it is delta x, but we're going to go ahead and jump right to the integral where we're going to let delta x approach zero and we'll call it dx instead. So we'll cross that guy out and make that a dx. So what does our volume element look like then? It's got a thickness of dx and a radius of r of x, which in this case is the function f. And so what's the volume of a disk? Well, it's just going to be the cross-sectional area, which is pi r squared, times the thickness, which is dx, right? So if we added up a volume element, here it is, right? Our volume element is going to look like dV is just going to be, let me write it out this way. dV in this case, that's just one individual little disk, right? That's equal to pi times r of x squared times dx. That's the cross-sectional area times the thickness, right? Isn't that how you get the area of a cylinder, is the cross-sectional area of the base times the height, right? Okay. Well, yeah, okay, but the pi is a constant, so we can pull constants out in front. So when we're adding up dv, we're just, really that pi starts off inside, but we're going to move that pi outside because it's a constant, right? Makes things a little simpler, makes the integral look simpler then, okay? So let's try an example. Oh, and by the way, just I want to show you, so what if we took a shape like this, right? What if we're doing this f of x from a to b? Does it matter that part of the function's under the curve? Like, do I have to take the absolute value of that function so it's all positive? No, I don't have to. Doesn't make any difference. When I revolve this thing around, I'm going to get the same, it's going to carve out the same volume either way. So you don't have to do this. That's just extra work for nothing, okay? No, you don't need to, exactly, right, because it doesn't matter if the curve is below or above the axis. When I rotate this thing 360 degrees, it's still going to carve out the same volume, right? Okay, say it again. Well, it's not even because it's squared, it's because right, right. It's because I'm creating. I mean, you can just kind of visualize this, right? If I take this whole shape and I twist it around 360 degrees, how much volume am I going to gouge out? Well, the top part is going to gouge that piece out. The bottom part doesn't matter if it starts below or above, it's going to gouge out that volume right there, isn't it? Right? So it doesn't matter. Doesn't matter. You don't have to worry about making sure everything is positive. So let's look at an example here of the disk method. So what if we start off with one where this time our function is y equals the square root of x. We're going to take the area defined from x equals 0 up to 5, and we're going to revolve that around the x-axis to carve out kind of like a, I don't know, looks like a space capsule tipped over or something, right? I mean, you get what I'm saying here, right? And we want to find that volume. Okay, well, how do we do it? Well, we've got to add up all the disks that we create. So what are our disks? What's going to define our disk? Well, the radius of the disk is just going to be, in this case, square root of x, isn't it? Everybody agree? It's just defined by that function. So r of x is going to equal the square root of x. Okay, and let's use I'm going to use my stuff instead of the textbook stuff, right? So r of x equals the square root of x. So a little element of volume, a disk in this case, is going to be pi r squared dx, right? Everybody see that? That's going to be the volume of an individual disk, right? This is the pi r squared is the cross-sectional area of the disk, and the thickness is dx, okay? Well, if we want to find the total volume, we're just going to integrate those little infinitesimally small volume elements. We're going to add those up or integrate them from x equals 0 to 5, right? Because really all we're doing is making an infinite bunch of slices from 0 to 5, and each one of those infinitesimally small slices is going to get revolved around the x-axis to create a little disk, and we add all those up, right? So I do have a little, I have a little way that we can visualize this. I hate to take the time, but it might be useful to see. Okay, so question. Because I'm adding up. Like are you getting the idea that when we do a definite integral, we're just adding a bunch of things up? So when we do this, if I'm taking the integral of dv, what's that mean? Integral just means I'm summing up all of those dv's starting at 0 and ending at x equals 5, right? So here's what it looks like. So it looks like this. Okay, so there's our function, right? There's our function. Now let's look at this. Let's look at an individual trajectory first. So let's see, how do I do this again? I want to go, yeah. See, I'm going to revolve that little rectangle around to carve out a disk. Everybody see that? Okay. Everybody get that? Okay. So what if we do, let's do a bunch of washers here. So if I only use 4 washers, then, oops, hang on a second. If I only use 4 washers, that doesn't match very well, right? That's not going to be, that's not the exact volume, is it? Right? If I use 4 washers. So let's let the number of washers get dramatically bigger. Like if I use 25 slices, right? Or not washers. I'm sorry, these are discs, not washers. We haven't done washers yet, right? These are discs. If I use 25 discs, okay, that's not bad, right? That's a pretty good approximation of our space capsule, tipped over space capsule. And if I use like 50, I mean, that's getting pretty accurate, right? That's the most I can do on here is 50. Okay, but if I use an infinite number of them, it's just going to look like, that, right? Well, I mean, it looks like it does actually give you finite pieces, but imagine that those are infinitesimally thin, then it's going to perfectly match the exact volume, right? Okay, so all we've got to do then is just do that integral, right? We set it up. We're adding up pieces of volume in the form of disks. The volume of each disk is pi x dx. So I'm just going to integrate those as x goes from 0 to 5. Easy. Pull the pi out front. The integral of x dx is x squared over 2. So I'll pull the 2 out front, right? And then I'm just going to evaluate that from x equals 0 to 5. So I get pi halves times 25 minus 0. 25 halves pi is my exact volume of that volume of, of revolution. Okay, make sense? Okay. So let's look at another example. What if we want to look at one like this? Okay, same kind of thing, right? So this time I'm defining the function is x cubed, and we're going from x equals -1 to +2. Okay, well, it's same kind of stuff. I'm creating disks. This time, what's the radius of my disk going to be? X cubed. Yeah, right? And the thickness is dx. So a volume element just looks like, uh, it's just going to be pi times x cubed squared, right? The radius squared times dx. So it's just pi x to the 6 dx. That's the volume of one little disk, right? Just going to integrate to sum all those up from -1 to 2. It's an easy integral, right? I just get the integral of x to the 6th is just x to the 7th over 7. Pull the 7 out front and right from -1 to 2. Plug it in and you get 129 sevenths pi. It's the exact volume. Isn't that super cool that we can do that? Okay, now this is going to hold on to your hats here. Now we can also revolve these around the y-axis. What does this mean then? Well, that's no big deal. Like we can do all the calculus we've done with areas under curves. We could do those sideways too. Only instead of having functions of x, we would just have functions of y, right? So in this case, like we're going to define our function as a function of y, x equals g of y, okay? And we haven't really talked much about that this year, but you've done a bunch of this in the past, right? And if I want to add up the area under the curve g of y, what's, from C to D, what does that look like if I've got functions of y? The area under a curve that's a function of y is just going to be the area between the curve and the y-axis, which is all we did with functions of x, right? When we said under a curve, we just meant the volume or the area trapped between the function and the x-axis. So a convenient way to say that is under, right? So really under in a sideways sense means to the left of, okay? But you get the idea, right? It's just between the function and the axis. In this case, the y-axis, because we're talking about functions of y, right? So then if I want to revolve this area around the y-axis, well, I'm still just going to create a volume of revolution that looks like this pedestal table, right? This one's standing up, right? Because we're revolving around the y-axis. And if I want to add that up, I'm still just going to create disks, only this time my disks they're disks that are rotated about a vertical axis instead of a horizontal axis, right? So the width, instead of being dx, it's dy, and the radius, instead of being a function of x, it's just a function of y, okay? Make sense? Okay. So that's what we get then. The volume by the disk method for revolutions about the y-axis would just be pi times the integral of r of y squared dy as y goes from c to d. So let's look at an example. Okay, if we look at an example like this, like we're going to pick the function y equals x cubed. We want to take the area bound by y equals x cubed, the y-axis, and the lines x equals 1 and x equals 8, okay? And we want to revolve that around the y-axis to create this shape, okay? Well, if we're going to do that, if we're going to revolve around the y-axis, we need a function of y. So I would have to just solve for x and isolate x, right, to write x as a function of y. And I would just get x equals the cube root of y, or y to the 1/3. So then our volume element, dv, is just going to equal pi times r of y, which is the cube root of y, we said, squared, times dy. Well, that's just pi y to the 2/3 dy. That's the volume of my disk that's rotated about a vertical axis. Okay, so the disk is oriented horizontally this time, right? And if we add all those up, well, we want to find the total volume. We're just going to integrate our little disks, but from y equals 1 to 8 this time, right? Because now our slices, how come? Because our slices are slices through the y-axis, right? So our slices start at y equal 1 and they end at y equals 8, okay? No big deal. So we get all this new free calculus for, doing nothing. It's just the same stuff, just with functions of y instead of x, which opens up a lot of opportunities for us when we're doing revolutions, okay? So then what do we get then? We get integral of y to the 2/3 dy from 1 to 8, pull the pi out front. Well, that's an easy one, right? We just get y to the 5/3 times 3/5. Pull the 3/5 out front with the pi, and we'll evaluate y to the 5/3 from 1 to 8. And what's that give us? 32 minus 1 times 3/5 pi ends up being 93/5 pi, and that's an exact volume for that. Okay? See how that works? Okay, so then we know how to do disks, and you get a little practice with this in the assignment. We know how to do disks now that are sliced horizontally or vertically, okay? And remember, like if we're making vertical slices, always think of what's the axis that we're going to slice through with our slice. If we're slicing through the x-axis, then these are going to be functions of x. Yep. If we're slicing through the y-axis, then they're going to be functions of y. If we're doing disks, right? Okay, well, what happens if we have a shape now where we're looking at an area that's an area between two curves, right? This time it's not just an area under a curve, it's between two curves. So what if we're going to define this area as being the area between f of x on the top and g of x on the bottom? And we're going to look at this area bounded from x equals a to x equals b. So we've got this area now that's kind of up above the x-axis, and we want to revolve that around the x-axis. Well, now what kinds of shapes would we make? If we took little cross sections of our area this time, and I rotated those or revolved those around, wouldn't I just create washers, right? I'd create washers like this. And what's the volume of a washer? Well, the volume of the washer is just going to be the disk. I'm just going to start with the disk with the big radius, calculate that volume, and subtract the core that I cut out with the small radius, right? So the volume of a washer then is just going to be pi times capital R squared minus little r squared, right? I get pi r squared dx, pi big R squared dx minus pi little r squared dx. We'll factor the pi out, factor the dx out, and that's what a little volume element looks like that's a washer. Okay, everybody get that? Does that make sense? So then I'm just going to sum those up, right, by integrating. So the volume by the washer method is just going to be pi times the quantity capital R squared minus little r squared times dx from A to B. Okay, so here's an example. What about one like this? Okay, so we're doing, these are about the y-axis. Okay, that's fine. We can do washers about the y-axis. If we're going to take this volume or this area that's defined by y equals 2x, the red line, and y equals x squared, the blue parabola that's enclosed by that, and we want to revolve it around the y-axis, then we're going to be making horizontal slices, okay? And we're going to create these washers that are going to be sitting horizontally in space instead of vertically, right? Because we've created them by rotating or revolving around the y-axis, okay? No big deal. So then what would my outer radius be? Well, that's going to, if we're revolving around the y-axis, the bigger radius is going to be created by the blue curve, right? X squared. And the smaller radius, the inner radius of our washer, is going to be the red line. Everybody see that? Okay. So then here's our formula. Volume of a washer, we're just going to sum up all the little dVs by integrating. So pi times big radius squared minus little radius squared, all times dy. Okay, but we were given these functions as functions of x, right? We need to turn these into functions of y. That's easy to do. If I write the blue function as a function of y, if I solve for x, what do I get? X equals y over 2. Oh, that's the line, isn't it? Sorry, that's the red function. So there's my inner radius, right? Y over 2. What about the outer radius? Well, if I solve for x here, I'm going to get x equals plus or minus the square root of y, but we've got positive the square root of y, don't we? Right? That's going to be the one that's above the y-axis, meaning to the right of it, okay? Okay, so then what do we get? So integral pi times the integral of the outer radius, which is the square root of y squared, minus the inner radius of the washer, which is y over 2 quantity squared, dy. So that becomes a y. What'd I do? Okay, this becomes y squared over 4, right? And I'm just doing that integral of the quantity y minus y squared over 4 dy, pi out front from 0 to 4. Okay, well, integral of y is y squared over 2. Integral of y squared over 4 is y cubed over 12. We're going to integrate from 0 to 4. So we got this pi out front. When I evaluate this at 4, I'm going to get 8. I'm going to get 16 over 2 is 8. If I evaluate y cubed over 12 at 4, I'm going to get 64 over 12, which is 16 over 3. Right? So there's everything I get when I plug in a 4. If I plug in 0, I just get 0, right? So simplify that and you end up with 8/3 pi. exact volume. Okay. And then, so give me 1 to 5 so far. Is that making sense? Okay. Yeah, I know you got to do some problems. Last one is, what if we're going to revolve something about an axis other than one of the coordinate axes? That's no big deal. Like, so what if we're going to model, or what if we're going to revolve the area defined, same area as last time, right? Defined by the line y equals 2x and y equals x squared. So we've got this area. But instead of revolving this around the x-axis or the y-axis, we're going to revolve this around the line y equals 5. Okay. Well, y equals 5 is a horizontal line just like the x-axis, isn't it? So wouldn't everybody agree then, if I'm going to do a revolution here using discs or washers about a horizontal line, I'm going to have to make vertical slices because my slices have to slice through the axis perpendicularly, right? So these are vertical slices. Well, vertical slices are functions of x, right? Because vertical slices cut through the x-axis, right? So now what's that look like? Okay, so here's one of my slices, right? Here's one of my slices that I'm making, my vertical slices through this area between the red and the blue curves, okay? So if I'm revolving it around the green axis, well then the biggest radius is going to end up being the blue distance in this case, right? The distance from the green axis to the blue curve down to the blue curve. Okay, what is that distance? Well, you tell me, what's that distance from y equals 5 down to y equals x squared? 5 minus x squared, isn't it? Right? It's the complete distance minus x squared. Yep. We're revolving around the green line this time. Okay, so we're creating washers where the core of the washer, the line through the center of the washers is no longer the x-axis. Now it's just a parallel axis. It's like we've taken the x-axis and just scooted it up to y equals 5. Okay, and the inside radius would be the smaller distance from green to red, which would just be 5 minus 2x, right? Okay, so everybody see that? So the outer radius becomes 5 minus x squared. The inner radius becomes 5 minus 2x. And now I just use my washer approach, right? Everybody gets, I mean, we're making slices through the x-axis. So that is our beginning. That is the definition of volume by washers, is that pi times integral of outer radius squared minus inner radius squared dx over whatever my limits of integration are. We're going from 0 to 2 in this case. How come 0 to 2? Well, because the intersections start at x equals 0 and they intersect up here at x equals 2. Yep. No, this is going to be a much bigger volume because these radii are much bigger. See, look, if I revolve around the x-axis, I'm creating a pretty small washer. Here I'm creating really big washers, right? So much bigger. Okay. Yep.
Why would it be 5 minus x squared, although it's not like all the way from the x-axis? So
okay, well, yeah, because what we're trying to do here is we're just trying to define this distance right there, right? So what is that distance from there down to there, that light blue line segment, right? Well, that distance is just the total green distance from here. Everybody agree from here, from there down to there is 5, right? And this distance right here from there down to there, well, that's just x squared, right? See what I'm saying? Because that's the height of the curve. The curve is x squared. So we're just taking the total distance minus that little distance that we're cutting off the bottom, and we get 5 minus x squared. Okay. Okay, so then, and then same thing here, right? 5 minus 2x, okay? And if all we got to do is just expand that out, 5 minus x squared expanded out is that. 5 minus 2x squared, quantity squared, expanded out is that. Distribute the negative, combine like terms, and we get that. Just some algebra, right? So if I integrate each of those terms, those are just power rule applications, right? Integral of x to the fourth is x to the fifth over 5, negative 14x squared. That's going to be negative 14x cubed over 3. Integral of 20x is 10x squared. And just evaluate that whole expression from 0 to 2. At 2, we get all that stuff. At 0, we get 0, right? And if I just add up all those fractions, I get 136/15 pi, which is the correct answer. That's the exact volume, okay? I think I've got a little model. We can look at this one a little bit. These are a little tricky to kind of visualize at first. But here it is, right? If I, first of all, so Maria, I want to show you what happens if I rotate this. See, look what happens. I'm creating a pretty big volume, right? Because the radiuses are big. So I'm creating a bigger volume total. It's almost easier to see if we look at like just one little cross section. Here, I'm gonna do a little trick here. Let's do one little cross section. Let's revolve. Okay, look at that washer compared to what happens if we revolve this around y equals 0. Okay, look at this washer. That's much smaller, right? Everybody see that? Yeah. Because they have the same thickness, right? That's got a way bigger cross-sectional area though. So it's got a bigger volume. Okay? Make sense? Say it again. Well, anytime you want to find a volume that has rotational symmetry like that, you can, yeah, you can. To do really complicated ones, that would require multivariable calculus. But I'm going to show you another technique tomorrow where we can add up some volumes. They have to fit some conditions, but we can add up some volumes by integrating that don't have rotational symmetry also by using the method of slicing, which I'll show you tomorrow. And then that's it. Then the one thing I want to plug in after, Tuesday's AP test, so we'll let people go do the AP test. And then I'll show you what would happen if, see if you can just kind of visualize this right now. Like, what if I were going to take this slice? So I'm going to take the area between these two curves, and I'm going to revolve this around the y-axis. Well, I could do horizontal slices and create washers, right? Like we did in the last example, right? That's what we did in this example right there. Agreed? Okay. I could also do this. I could also take vertical slices, and if I revolve those around the y-axis, now I'm not creating washers, I'm creating little shells, right? Like imagine when you recycle your aluminum cans and you cut the bottom out of the can and the top out of the can so it's like a tube. What if I stacked a bunch of those concentrically? I could create a volume of revolution that way too, using shells instead of stacking up washers or discs, right? So we could also add up a volume by summing up shells with an integral. Okay, why would we want to do that? Well, look, that gives us two ways of calculating the same volume, right? Sometimes it's easier to deal with functions of x, and sometimes it's easier to deal with functions of y. So you could take your pick if you have that other method also. You can pick the method that's going to make the calculus easier, right? Okay, but that'll come next week. All right.